Yo, what's up everyone? Welcome to States of Matter Part 1. A good understanding of states of matter requires an understanding of intermolecular forces. So intermolecular forces are forces that occur between molecules that keep them together. So for example, if you had like a molecule of H2O, if you had a molecule of H2O, it would look something like this. And within the molecule, you would have, covalent bonding or ionic bonding if you had other compounds. And between the atoms themselves, you have some sort of intramolecular forces. Intramolecular forces. And that's what's keeping the atoms together. However, between multiple molecules of water or any other compound, you're going to have intermolecular forces. And these are forces that occur between the molecules that keep them together. Now, it's important to note that these intermolecular forces are going to be weaker than ionic or covalent bonding, but since you have so many of them all around every single molecule, you have this net force that is strong enough to keep them all together. Now, if you wanted to see intermolecular forces in action, you could look at something like a heating chart. So a heating chart is what happens to a compound at the phase of a compound as you constantly add some energy. So if you had something like water, if you had it start in ice form and you put it under a flame, what would happen is that the temperature would start to go up. It would be in its ice form. It would start to go up and then it would plateau. Why does this happen? Well, remember, temperature is just a measure of how fast the molecules are moving. When it's in its ice form, the intermolecular forces are really strong. So they get to a point where they're moving around pretty fast, but they can't move around any faster unless they break more intermolecular forces. So what happens is that although you're constantly adding energy, that energy isn't going towards increasing the temperature. It's not going towards making the molecules move faster. Instead, it's going towards breaking those intermolecular forces. And when you've broken enough intermolecular forces, the water goes from the solid ice state to the liquid normal water state. And from there, it increases in temperature as you continuously add more heat, and it then reaches the same dilemma. It starts plateauing off because you need to break more intermolecular forces. And it does that, and once you've broken enough intermolecular forces, you now have steam and you can increase the temperature even more. You can make the molecules move even faster. So that's how you can read a heating chart to understand intermolecular forces. Now, intermolecular forces are going to be mainly Coulombic interactions. These are interactions between two charged particles. And you probably have some sort of intuitive understanding of this already. So if I told you had two positively charged particles, you would know that they repel each other. And it's the same with negatively charged particles. They also repel each other. But if I give you a positive and a negatively charged particle, you know that they would attract each other. And that force of attraction is equal to K times Q1 times Q2 over R squared. K is some sort of constant. Don't worry about K. Q1 and Q2 represent the charges of the different particles. So as you increase your charge, your force goes up. The attraction between a -1 and a -1, the force of attraction between this system is lower than the attraction between this system. And that's because their Q1 times Q2 value would be greater. And then this is all over R squared. This tells you that you have an inversely proportional relationship between the force of attraction and the distance between your two particles. And also it tells you that you have not only an inversely proportional relationship, but it's a square inverse. So as you increase the distance linearly, the force of attraction goes down exponentially. All right. Now that we understand that intermolecular forces are going to be Coulombic interactions, let's start talking about the intermolecular forces themselves. You're going to have 6 main types of intermolecular forces, and this is the order starting from the most intensely strong intermolecular force and then going all the way down to the weakest. So ion-ion forces are going to be the strongest, and London dispersion forces are going to be the weakest. Let's start with ion-ion. So an ion-ion interaction is the most pure form. It's purely Coulombic. You have a positively charged particle reacting with a negatively charged particle. This is what happens if you look at something like sodium chloride. So sodium chloride is in this lattice structure, and you have the positively charged sodium ions being attracted to the negatively charged chloride ions. And this is just an ionic interaction. They're really strong. These are really hard to break up because they are purely Coulombic. So ion is really simple. The next one that you're going to have is an ion dipole. A dipole is a molecule with an unsymmetric distribution of positive and negative charges. So if you look at a diagram, you're going to have different electronegativities of different atoms. Electronegativity is a atom's want to attract electrons. If you have a really electronegative atom, when it forms a bond with another atom, it's going to want to attract most of the electrons to itself. And because of that, you sometimes have an uneven, splitting of your electrons. You have an uneven sharing. What that causes is that you have some net dipole moment. For example, if you look at the H2O molecule here, the oxygen is attracting a lot of the electrons. So around the top is where you have a negative charge, and around the bottom is where you have some sort of positive charge. The same happens in this carbon dioxide molecule here. The oxygens are attracting the electrons towards itself, but since you have both of them on both sides, it's kind of like a tug of war where you have a stalemate where both sides are just as strong. So you don't have a dipole happening at the carbon dioxide here, but you do have some sort of dipole happening on the water here because the oxygen is stronger than the hydrogens when it comes to attracting electrons. Now, when you have some sort of dipole, you can, simplify the diagram by kind of putting a positive on one side and a negative on one side. So in the case of the hydrogen fluoride here, the left side is positive and the right side is negative. And you can signify that using these symbols. This is a delta plus and a delta negative. So when you have some sort of dipole and it comes around this ion, they attract each other. And you can see like a really cool GIF here of a positively charged ion being attracted to one side of a dipole and a negatively charged ion being attracted to the other side. So this is a ion dipole interaction, and they're weaker than ion because the dipole is a weaker Coulombic charge. So it goes back to the Q1 Q2 thing. The charge of the dipole is weaker, so a ion dipole is weaker than an ion. If you're following, then you can probably predict what the next one is. It's going to be a dipole. So you have one dipole being attracted to another dipole. So if you have a dipole facing this way where the positive charge is on the right side and the negative charge is on the left side, if you face another dipole in the opposite orientation, if you have negative on this side and positive on this side, the dipoles are going to attract each other. And it's the constant formation of these dipole-dipole interactions that hold molecules together. So that's a dipole-dipole. It's weaker than an ion dipole. And again, it's because the charges of the dipoles are weaker than in an ion form. All right, let's talk about, by the way, dipole-dipole attractions are about 1% as strong as covalent and ionic bonds. So this really goes to show you that intermolecular forces are much weaker than intramolecular forces. All right, let's talk about hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole attraction where a hydrogen is electrostatically attracted to a highly electronegative atom. And there's three highly electronegative atoms that can form hydrogen bonding. And that's going to be fluorine, oxygen, and nitrogen. So when you have a dipole-dipole interaction where a hydrogen is attracted to either fluorine, oxygen, or nitrogen, it's stronger than normal, and we call it a hydrogen bond. Why do these in particular cause hydrogen bonding and others don't? Well, there's going to be mainly two reasons. The first one is the fact that the electronegativity is really high. When you have a really high electronegativity, what that means is that when the atoms go to share the electrons, there's a really uneven splitting of your electrons. So if I give you a hydrogen and a fluorine wants electrons all to itself. So it'll make a really strong negative pole and a really strong positive pole. What that means is that your charges, your Q1, Q2, is going to be really high. So when you have a really electronegative atom, the electrons are a lot closer to, are a lot more localized to one side as opposed to another, and you have a really strong dipole. The second reason why hydrogen bonding is so strong is because of the size of the hydrogen atom. So you can imagine a dipole of one of these compounds. Let's say it's positive on this side and negative on this side. You can imagine the hydrogen being able to get really, really close to that dipole. And the reason it gets really close is because, again, it's really small. So the nucleus of the hydrogen is what's being attracted to the electrons of the dipole. And since they're so close, you're maximizing your force of attraction. Remember, your force of attraction was equal to K times Q1, Q2 over R squared. And when you make R really, really small, your force goes up exponentially. So that's the second reason why hydrogen bonding in particular is such a strong dipole-dipole attraction. First is because of the electronegativity, and that's creating a really strong dipole. And two is the size of the hydrogen. So the hydrogen, the size of it's allowing the dipole and the hydrogen to get really close, and you have a dipole-dipole attraction. All right, the next type of intermolecular force I want to go over is an ion-induced dipole. And this is when an ion induces a nonpolar compound to turn into a dipole for a small moment of time. Okay, so imagine you have a nonpolar compound. You have a compound here, and nonpolar means that there's an even distribution of electrons. So you can imagine there being an even amount of electrons on both sides of the compound. It's all even. But you have to remember that these electrons are not just sitting there. They're free to move, and they can move based on what type of outside forces impact them. So let's say I introduce some sort of ion into the mix. Let's say I introduce some positive ion here. What's going to happen between the ion and the electrons? Well, the ion is a positive charge, and the electrons are a negative charge. So what that's going to cause the compound to do is it's going to cause the electrons to move towards one side as opposed to another. The electrons are being really attracted to the positive charge, so you have a sort of dipole that's happening here. The ion is attracting the electrons, so now this compound is no longer nonpolar. You can see a dipole form here. There is a stronger negative charge on the right-hand side and a stronger positive charge on the left-hand side. So this ion has induced a dipole. And now that you have some sort of dipole, you have some sort of attraction between the dipole and the ion. So this is an ion-induced dipole. The ion has induced a nonpolar compound to become a dipole, and because of that, you can have some sort of interaction between them. The next one is really similar. It's a dipole-induced dipole. So it's the exact same thing. You have some sort of nonpolar compound with an even distribution, and you have some sort of dipole. Let's say the dipole looks something like this. What is the dipole going to do to the compound? Well, it's going to cause the electrons in the nonpolar compound to move around. The electrons are attracted to that positive charge, and so you have an uneven distribution of electrons. And again, this is going to cause a dipole. So there's a negative charge on the right side and a slight positive charge on the left side. So that's again another dipole, and now you have a dipole-dipole interaction. Now, there doesn't always need to be some sort of ion or dipole to cause this to occur. Let's say I have some sort of nonpolar compound here, and there's an even distribution of the electrons. Again, remember that these electrons are not just stationary, they're free to move, and they are constantly moving. So let's say there's a moment in time while all the electrons are moving that there's more electrons on one side as opposed to another. Let's say there's more electrons on this side as opposed to the other side. Well, what that's done to the compound is that it's become a dipole for a slight moment of time. There's a partial negative charge on the right-hand side and a partial positive charge on the left-hand side. We call this a temporary dipole moment. For a split second, the nonpolar compound has turned into a dipole, and the fact that it's a dipole is going to cause more dipole-induced dipole. So this dipole is going to cause other nonpolar compounds around it to turn into a dipole, and you have a bunch of these dipoles forming, and it's for the split second of time. That is exactly what we call a London dispersion force. It's the constant formation of these dipoles to create a weak intermolecular force that holds together all compounds. And remember, this is all by random chance. By random chance, the electrons can move to one side as opposed to another. Some molecules are going to have more London dispersion forces than others. And it's usually going to be as atomic number goes up, so does London dispersion forces. Why is this going to happen? Well, as you increase the number, your atomic number, you're also going to be increasing how many electrons you have. The more electrons you have in a compound, the more likely it is that by random chance, more electrons are going to be on one side as opposed to another. When that happens, you have a higher likelihood of a dipole forming. And when you increase your likelihood of a dipole forming, we say that increases polarizability. That's that P here. And as you increase your chance of dipoles forming, as you increase polarizability, so do you also increase your London dispersion forces. So bigger compounds with more electrons are going to have more London dispersion forces than smaller compounds. But remember, London dispersion forces are the bottom of the food chain. They're really, really weak. And a lot of the times, even though a compound is smaller, it's going to have stronger intermolecular forces because it's going to have, dipole-dipole interactions, or it's going to have ion-dipole or ion-ion. So London dispersion forces are not the end-all be-all. One last note is that as your intermolecular forces go up, so does the boiling point of the compound. This is what it means. As you have more and more intermolecular forces, the molecules are more tightly bound, so it takes more energy to break them apart. And that's it for intermolecular forces. If you have any questions, feel free to send me an email or leave a comment or something. I hope this was helpful, and I hope to see you later. Thank you.